we're going to start here by talking about section 8.7, which is 3D vector equations of a line. The nice part about the move from 2 dimensions to 3 dimensions is that the vector equation for the line does not change. It's simply r is equal to r naught plus vt, where t is a scalar. Remember, r is representing our point vector and v is representing our direction vector. So let's do an example. Find a vector line equation through the point 5, -2, 6, and -3, 4, 1. So remember that r naught is our point vector, so it doesn't matter which vector we use. For the sake of argument, I'm just going to use the first one. And then our direction vector, in 2 dimensions we use slope to give our direction vector, but here we don't have slope in 3 dimensions. So in 2 dimensions, the direction vector we used was we used slope to find the direction vector. In 3 dimensions, we don't have slope because we don't have rise over run, because there's 3 dimensions in which the point is changing on our line. So what do? Well, if we think about it, basically if we have a point and a point, we need, that would be a direction vector, or that would be a direction vector. So all we really need to do is just use the head minus tail rule to come up with a direction vector. And it doesn't matter which order we use or which vector or point we use as the head or the tail, because either of these two, whether it's going from one point to the other, the reverse direction, is still going to be fine. So let's just say we're going, I usually just go with the first point as the head and the second point as the tail, just because I don't goof up the order halfway through. And I just switch to a column vector because it was a little bit more compact there. But are done. So no big deal. So the direction, when we have 2 points, is really easy. We just find a vector that goes between the 2 points. So that's not a problem. Next, let's look at another example. So in this question, we're asked, does the point -5, 6, 11 lie on the vector line equation R? And this we're going to do just like we did in 2 dimensions. I'm going to start by just doing the vector addition. So I'll do the scalar multiplication and then do the vector addition. I should say the vector operations is what we did. So scalar multiplication first, then vector addition second. So all this is saying then is I need to check to see if the value that gives me, the value of t that gives me -5 in the x-coordinate is the same as the value of t that gives me 6 in the y-coordinate, is the same as the value of t that gives me 11 in the z-coordinate. So all we're going to do is we solve for t in the x direction. We solve for t in the y direction. And we solve for t in the z direction. And because we have the same value of t each time, we can conclude, yes, this point does lie on our line. If one or more of the t's are not the same, then we can conclude that point does not lie on that line. that does it for section 8.7. So in section 8.8, that's what we're going to work on now. We're going to be talking about the intersection of two lines in 3 dimensions. So there are 4 things that can happen. The first thing is that the lines can be parallel and non-intersecting, or non-overlapping. So imagine the lines are in the same plane. Basically this. Lines can be parallel and overlapping. We sometimes call this coinciding. So imagine the 2 lines are in the same plane. One line is right there, and the other line is right there on top of it. The third is intersecting. So again, imagine the 2 lines in the same plane. They intersect. And the fourth, this is different from 2 dimensions. At this point, these 3 other outcomes are the same outcomes that you could get in 2 dimensions. The last outcome, though, is lines that are not parallel and not intersecting. So imagine something like this. So we have these lines M and N that are in distinctly different planes, and they're obviously not parallel because there's no plane that I can draw that's going to contain both lines in which they would be parallel. So that's our 4 outcomes. So what we're going to do with these 4 outcomes is I'm going to start by kind of building out a flow chart to describe or for us to sort out which situation we're into. Okay? So the first thing we'd want to check is, are the lines parallel? To do that, I want to see if the direction vector for line 1 is equal to a scalar multiple of the direction vector for line 2. I guess we should say this, that we'll say this is R1 and this is R2. Okay. So if those 2 directions are scalar multiples of each other, we check, are the lines coinciding? To do that, what I want to check is that if the point vector from line 1 is on line 2. If yes, then we're coinciding. If no, then we're parallel. So that would be non-overlapping or non-coinciding parallel. Okay, let's go back to our no branch way up here. what we'd check then is, are the lines intersecting? Remember, this was something that we did for 2 dimensions in a previous section. So to do that, oops. Sure I did that right. Okay, so use T there. I need to check to see if the line 1 and 2 share in a point of intersection. If it's yes, we then should find that point of intersection. And report the lines intersect at whatever that point was. If the lines do not intersect, then we know then these are non-parallel, non-intersecting. Okay, so just to zoom out and take an overall view, every single time, the first thing I do is I check to see if they're parallel by seeing if one direction vector is a scalar multiple of the other. If they are parallel, if the lines are parallel, then I want to check to see if a point from one line is also a point on the other line. And it doesn't matter if I take a point from R1 and check if it's on R2, if I take a point from R2 and check if it's on R1. If that point is on the other line, then the lines have to be coinciding. And if not, then they're parallel. Alternatively, if the lines were not parallel, I need to check to see if they have an intersection by seeing if there's a point on both of these 2 lines. If they are, then I would find the point and say they're intersecting. If there is no points on both lines, then I'd say they are non-parallel, non-intersecting. So this is a process that I expect you to kind of have memorized as to what to do. Okay, so I built this flow chart for you to help kind of remember what to do when and the order of you need to do it. But there's essentially just 3 tests to remember, right? So you just kind of need to remember the tests and the order of the tests and which one comes after, as the result of which. But it's not, once you've done it a couple of times, it's not too bad. Let's run through some examples now to practice this process. Okay, so let's say we have the line R1, which is the vector 2, 3, 3 plus 4, negative 12, 16 times t, and R2, which is the vector 3, 0, 7 plus negative 1, 3, negative 4s. So the first thing I want to do is I want to check to see if the vectors are parallel. So I want to look at my 2 direction vectors and see if one of them is a scalar multiple of the other. Now, I would say here I can do this just by inspection, because I notice that negative 4 times negative 1 gives me 4. Negative 4 times 3 gives me negative 12. And negative 4 times negative 4 gives me 16. So basically all I did there was this check is yes, right? The k in this case is negative 4. So that was really easy. That check is super easy. It's easy to do. It's the first thing we do every single time we're doing one of these. So don't forget that one. Once we have this now, we need to check to see if one of the line, or a point from one line, is on the other. So let's say we're going to take the point vector from R2 and see if it's on R1. So we're just going to take our point vector from R2 and plug it into R1, and we're going to see if that is a point on R1. And we do this the same way we did before. We're basically going to see if there's one value of t that can give each of these three components. So 3 is equal to 2 plus 4t. 0 has to equal 3 minus 12t. And 7 has to equal 3 plus 16t. So if I do that, I get 1/4 is t. Here I get 1/4 is t. And here I get 1/4 is t. Since these are all the same, I know that R02 is on R1. So we have that these are coinciding. And we're done. Let's do another example. Okay, so here we're going to check for the two vector line equations. R1 is 2, 4, 1 plus 4, 5, negative 3t. And vector line equation 2, R2 is negative 2, negative 4, negative 1 plus negative 6, negative 9, 2s. Again, the first thing we want to do is check to see if the direction vectors are scalar multiples of one another. Here it's much more difficult to tell straight away, so I'm going to kind of do this systematically. So here I get negative 2/3 for k. Here I get negative 5/9 for k, and here I'm going to stop. Since these are different values of k, I know that they are not parallel. That value of k needs to be the same for all of them. So that tells me that these two lines are either intersecting or non-parallel, non-intersecting. In either case, I need to then see if they do share a point of intersection. So I'm going to set the two line equations equal to one another. And find the intersection of the two lines. And this is almost exactly the same process in 3 dimensions as it was in 2 dimensions. But there's one slight difference. So I start by just doing the vector operations to turn this into one vector. Oops, forgot my s. On each side. So I'll turn this now into a system, just like we did before. Okay. Now, when you look at this, though, we have 3 equations, but only 2 variables. So this is where a little bit of difference is going to come in. What we're going to do is we're just going to pick 2 of the equations to use to solve our system. But the answer for S and T that we get from that, we have to go back and check to make sure it satisfies the 3rd equation. So if I go ahead and solve this system, Just going to enter into a matrix just like we've done before. Some of the coefficients from my system are just going to become the entries in my matrix. So I've made my matrix. I'll exit back out, go back into the matrix menu. This time go to the Math tab, scroll all the way down till find the RREF command, and perform that function on the matrix A that I just made a moment ago. So using that, I get that T is 2 and S is -2. So before I go, though, I have to check to see if this works, and it does, right? So I have to check with the third equation and make sure that that still works. Now it does, so that tells me that these two lines are intersecting. But I need to find that point of intersection still. So to do that, I'm going to pick one of the S or the T, it doesn't matter. I'm going to choose to pick the T, and I'm going to go ahead and plug that back into my equation. Was it R1 or R2? I forget now. It's R1. So when I do that and I perform the vector operations, 4 times 2 is 8, plus 2 more is 10. 2 times 5 plus 4 is 14. And 2 times -3 plus 1 is -5. So my point of intersection would be 10, 14, -5. Okay, so that's a good smattering of examples. At this point, it's worth mentioning that the only difference between the non-parallel, non-intersecting is either this system has no solution, that could happen, or when I check the S and T for the third one, it doesn't check out. So either of those two things could happen in the no solution, or the non-parallel, non-overlapping situation. And at this point, we've now done everything we need to do to finish the chapter. So you guys can do all the way up to 122. And in particular, before next class, I would want, if I were you, to definitely try 119 through 122. Those are the intersections of lines in or the line interactions in 3 dimensions that we just talked about in this section. I would definitely want to take a look at those problems and try those problems before our next class. Definitely do that. Okay. But that's it for today. I tried to keep this short and sweet. Have a great day, and good luck on your homework.